Hi everyone, it's Mrs. Meehan, and in this screencast, I will go over static friction. So just to get started, imagine you're trying to push a very heavy box or any heavy object across the floor. Think about the following. Eventually, it starts to move. Which feels easier, pushing the box before it starts moving or pushing the box once it is moving? And does anything happen to you in the moment when the box finally starts moving? So take a moment to think about that. Okay, so hopefully you thought about the following. When you're pushing the box, how it feels before it starts moving versus after it is moving, typically it feels easier once something is in motion. So when you do push something heavy, in the moment when it's not moving yet, but you are pushing, you are applying a force, that feels a lot more difficult than when you are applying the force and the object is moving. And that's because you're actually applying the opposing force that is working against you is actually less once you start pushing the object, once it starts moving, than when you are actually trying to move it and it's not yet moving. And we'll examine that a little more today. Now, does anything happen to you in the moment when the box finally starts moving? Yes. So if you think back accurately, or if you're pushing a heavy enough object in that moment where it does start to move, sometimes you might actually fall forward a little bit because suddenly it's moving and suddenly it's becoming easier to move. So the amount of force that you were just applying is more than you need to actually keep it in motion against that frictional force. So we'll take a look at that as well. So some of the objectives with this lesson is that you'll solve problems involving multiple forces and accelerations not restricted to one axis of motion, determine whether a frictional force is kinetic or static, and solve problems involving static and kinetic friction. Now, static friction is a frictional force between two surfaces that are not moving along each other. So a force can be applied, but the object is not moving yet. There is something called static friction. It is what keeps an object from moving when a force is first applied. So before it starts to move, there is static friction. And remember, friction kind of comes back to those interactions at the atomic level between the two surfaces. There's a degree of roughness between them, and that results in the frictional force. Now, the static friction force, there is an equation to express it, and you'll notice it's kind of similar to the kinetic frictional force, but it's also a little different. So let's take a look. Recall that for kinetic friction, the equation is force of friction is equal to the coefficient of kinetic friction, mu k, times normal force. But you'll notice in the equation for static friction that we have an inequality instead of an equality, and the coefficient is different. So the coefficient for kinetic friction is actually different than the coefficient for static friction. So it's different for every pair of surfaces. Now note the inequality symbol in this equation. This is the less than or equal to symbol. So think back to that box that you're pushing on. So you're pushing on it until it moves. You can apply a small force. Nothing happens. You apply more and more force until the box finally starts moving. This is the maximum amount of static friction. So the friction can be less than the maximum amount or equal to the maximum amount, but never greater. The force of friction is equal to mu s times normal force at the instant when the object starts to move. But then what happens? The object starts to move and the kinetic frictional force takes over. So now that the object is moving, we are looking at mu k, the coefficient of kinetic friction, times the normal force. So again, static frictional force increases as the applied force increases, always equal to the net applied force. So until that object starts moving, the static frictional force is equal to the applied force, but up until a certain point, a maximum. On the graph to the right here, where we are comparing frictional force to applied force, here we have zero force. As you apply a force, let's say we're at 10 newtons here, the frictional force is also 10 newtons. And also note that this is while the object is not in motion. So we have the static friction equation up here. So static friction at this point is the type of frictional force that is occurring. So as long as the object is not moving, the frictional force is equal to the applied force. So now we're here to 20 newtons, and the frictional force equals 20 newtons. They are equal. You have a net zero force. They're canceling each other out. So there is no acceleration. There is no motion. Again, you keep applying force. You keep pushing and pushing on that heavy object. We're at 30 newtons. Then all of a sudden, you hit 40 newtons of force. This is that point where we are now starting to move. That object is now sliding. You'll notice there's a drop. And this is the point where you might fall forward a little bit because now suddenly the equation here, the coefficient for kinetic friction, is actually lower than the coefficient for static friction, which I'll show you in a bit on the next slide. But that results in a lower frictional force. And in this case, it is now a constant. It is always going to be the coefficient of kinetic friction times the normal force. So it no longer is related to the amount of applied force. You have now overcome static friction, and now we have a non-zero net force. So we have motion. So what you're seeing now is you continue to apply a force in increasing amounts, but no matter what, whether it is 50, 60, or 70 newtons, now the frictional force holds steady at 30 newtons. Let's take a look at the coefficients of static versus kinetic friction. So in the last lesson, you pretty much just saw this column. So remember that the coefficient of kinetic friction is essentially a percentage of the normal force, which is equal to weight. Normal force for horizontal motion that we'll be looking at is equal to mg, or weight. So this coefficient is a percentage of the weight of the object. So with kinetic friction for wood on wood, notice that's about 20% of the weight of the object compared to 40% here, 0.4, as the coefficient for static friction. So that is a much higher number. You'll notice that this is true as we go down, although it's interesting to note that we have Teflon on Teflon, and joints in human limbs are holding pretty steady. Teflon is about the smoothest surface we can get, or it's a very smooth surface, and joints in human limbs are very efficient and have a very low frictional force, whether it is static or kinetic friction. It's pretty easy to move. So once an object is in motion, it is easier to keep it in motion. That is explained by the fact that the coefficient of kinetic friction is typically much lower than the coefficient of static friction. Take a moment to watch this quick recap by Professor Dave Explains, comparing kinetic versus static friction. Okay, let's try a couple practice problems. So we have a 4-kilogram brick sitting on a table. The coefficient of static friction between the surfaces is 0.45. What is the largest force that can be applied horizontally to the brick before it begins to slide? Okay, so we're given some information. We know that the mass here is equal to 4 kilograms. And we know the coefficient of static friction is 0.45. And there's no units there. So what is the largest force that can be applied horizontally to the brick before it begins to slide? So we want to figure out the applied force. Let's take a look. So we know our new equation here. We have the force of friction. And since we want to find the largest force that can be applied, we'll set it as equal to the coefficient of static friction times normal force. So we're trying to find the largest force that can be applied. That's the point where the frictional force is equal to the coefficient of static friction times normal force. Now also recall that normal force is equal to mg. Always keep that in the back of your mind. So you're not told what normal force is, but since we know it's equal to mg, we can substitute mg for normal force. So you see now that we've rewritten the equation to replace that. So we have the equation written like this. Now you can just plug in the numbers because we're given the mass, we know the coefficient of static friction, and we know the constant here, acceleration due to gravity. So you plug in all of that information, and it looks like the maximum applied force before it begins to slide is going to be 18 newtons. Now the next question kind of builds upon that, so keep that in mind. A 4 kilogram brick is sitting on a table. The coefficient of static friction between the surfaces is 0.45. If a 10 Newton horizontal force is applied to the brick, what will be the force of friction? Okay, so this is the same problem, but instead of asking what the maximum applied force could be, it tells you that a 10 Newton horizontal force is applied to the brick. Now, what will be the force of friction as a result? So we have the force of friction is equal to the coefficient of static friction times normal force. We know normal force is equal to mg, so we can replace that part of the equation with mg. Now, this is just calculating the same thing from the previous problem, where we got approximately 18 newtons of force. Now, since the applied force we're given, and this is the maximum force you can have before the object starts moving. Now, the applied force that we're told is only 10 newtons. So it's asking what will be the force of friction when you apply 10 newtons? Well, we know that this object doesn't move until you exceed about 18 newtons or 17.64. The applied force that we're given, 10 newtons, is less than that maximum force of friction. So we know that acceleration is going to be 0. And recall that with static friction, it is always going to equal the applied force until you hit that maximum. So since we have not hit that maximum, which is about 18 newtons, it is 10 newtons, we know that the frictional force is going to be equal to that applied force of 10 newtons. Okay, so practice problems that go along with this lesson include chapter problems number 55 to 66 and the multiple choice problems number 35 to 38. So definitely practice those and let me know if you have any questions.